Let's see. According to this, let's see, where are we? I have horizontal tangents at the following angles. Pi over 2. The 7 pi over 6, which would be, by the way, here, because that's, you may catch that? Those are my 30-degree type angles in this. So I have horizontal tangents here and here, but then there's kind of a confusing one. The 3 pi over 2. It's going like that, isn't it? Do you think there's a horizontal tangent there? I don't think there is. I mean, there's a sharp point right there. Kind of keep that in the back of your mind there. That's kind of weird. All right, now how about the vertical tangents? According to this, the vertical tangents are at pi over 6, which would be here. Oh, beautiful. 7 pi over 6, which is here. Oh, beautiful. And again at 3 pi over 2. Houston, we have a problem. Did anybody notice this? I cannot have a horizontal and a vertical tangent at the same place. No, in fact, something way cooler than that.
Okay.
Aren't both numerator and denominator going to equal 0 at that point? Oh, if I put a 3 pi over 2 in here, I'm going to get 0 over 0. It's neither horizontal nor vertical, but visual inspection, what do I have there? Anybody know?
Undefined.
Well, no, the point is a cusp. The point is a cusp, and when I think of a cusp, I'm thinking more of a vertical tangent at the cusp. But the derivative doesn't actually exist at the, oh, okay, it's not differentiable. We know that from Calc 1. You're not differentiable at a cusp. But in this case, it's even weirder. Both the numerator and denominator go to 0, so my derivative has a removable discontinuity. Not the function, the derivative does. So I can't actually take a derivative there, but we do have a cusp there. So I have exactly 3 horizontal tangents, I have exactly 2 vertical tangents, and I have a cusp. But we could see the cusp. Now, if you were drawing this by hand, would you necessarily know that was a cusp? Would you necessarily know it was a sharp, pointy object there? Remember, when we did it using our polar graph, I mean, you had a point here, you had a point here, you had a point here, you had a point. You know, it could have, for all you knew, looked like that. I was saying, no, it looks like this. But now we know, okay, there's something goofy going on at the origin. It's cool, it's a cusp. So, do you think cardioids always have a cusp? Vertical or horizontally opening? Yeah, they'll always have a cusp. And the cusp is an interesting place because, again, I can't take the derivative there. But if I go back to Calc 1, I can't take derivatives at cusps in general, right? It's a non-differentiable point, but it's one of the more interesting non-differentiable points, okay? I'll remind you what it was in Calc 1. And by the way, the rules are still the same in polar. It's just a little trickier to identify. There's 4 types of non-differentiable points, and it's the same 4 in this case. The one you're not probably going to see is the break in the graph. So in Calc 1, right, we use things like piecewise functions. Remember doing that? It said, you know, f of x looks like x squared when x is less than or equal to 0. It looks like x plus 3 when x is greater than 0. And so therefore my graph looks like that. Okay. I have a break in the graph at x equals 0. It's continuous everywhere else. It's differentiable everywhere else, but the limit doesn't exist at 0. It's not, right? It's not continuous at 0. There's no derivative at 0. This is called a piecewise function. I defined it in stages. We don't like these in Calc 1, but they're perfect for illustrating things like continuity, right? Differentiability. It's really easy for me to demonstrate, oh yeah, I can't tell you the derivative at 0 because it depends on which side I am, right? I'm going to get different things. So that's one we didn't deal with a lot in Calc 1. We actually deal with this at the higher levels. We deal with this stuff in differential equations. We actually figured out a way to write this as one function. We can actually do this as one function. It's really cool. It's like an on-off switch. When I'm on this side, it's off. On this side, it's on. And you can write this as f of x equals and explain the whole thing. Something you're going to get to way, 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 way in the future. Okay, so that's the first one. That's the one we just never deal with much of. Then the second one, real easy one. Well, this is continuous for the entire right half of the number line. It's differentiable for the right half of the number line. So where does it get tricky? Right here. The derivative does not exist there. But the function is defined as 0. You're right, the function is defined as 0. What's the derivative of this? See that? Oh, 0 is not in the domain of the derivative, is it? It's in the domain of the function, but not the derivative, which means I'm not differentiable at 0. I have a vertical tangent there. No, vertical tangents are okay. I have an endpoint there. Vertical tangent is okay. We're going to look at that one next. I have an endpoint. Vertical tangent means I can't give you a value, but that one just stops. So if I was driving on a road, I'd hit a brick wall right there. I can't drive through it. So then what about, I'll write it as the cube root function. This is defined everywhere. It's continuous everywhere, but it is not differentiable everywhere. Again, it's not differentiable at 0 because it would be undefined. But I do have a tangent line at the origin, and it is vertical. So on this side, my slopes are increasing, 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 increasing. On the other side, they're increasing, increasing. If I was trying to ride my bike left to right, I'd be in trouble, wouldn't I? Right? I have a place near where I live where these kids have made all these dirt mounds. It's really funny. Huge dirt mounds for their riding their bike. And one of them is getting steeper and steeper and steeper. And I was walking my dog yesterday and I was watching. They didn't get hurt, and they were wearing helmets. But the kids, they kept trying to do it, and then they'd fall and wipe out. And then they'd try to do it, and they'd fall and wipe out. Because they were trying to ride their bikes up here and go to the other side. Well, you're never getting to the other side. Why? Because the best you can do is to go straight up in the air. Right? You can't drive. If you were in a vehicle, you couldn't drive through this. It's impossible. Okay? Because at some point you're going to be vertical and you're never going to be going forward at that point. So this one is the third type of non-differentiable point, even though the graph was continuous. And then the last one, which is by far the most interesting, is this one. Now, the reason I say this is the most interesting is because it's continuous and defined everywhere. I went small positive, steep positive, huge positive, vertical, back to huge positive. Everything seemed to be kind of consistent there. Small negative, big negative, huge negative, almost infinite. And then on the other side, positive. Ooh, these slopes are approaching positive infinity. These slopes are approaching negative infinity. That's really crazy, isn't it? And the derivative of this guy is what? That, which again, is not defined at 0, but in this case it's even worse. The derivative from the left and the derivative from the right aren't even going in the same direction. One's going up, one's going down. Woo. So these are the 4 types of non-differentiable points, but they have names. This is called a cusp, this is called a vertical tangent, this is called an endpoint, the other one's called a break. You need to know those because those are the ways you identify it. Or if you were reading it and it was already identified, you wouldn't have to do a lot of work. So when you were doing stuff in Calc 1, you were given functions, a lot of times you'd see things with fractional exponents. And you were trying to figure out where are the critical values, right? Where's it increasing, decreasing, inflection points, all that kind of stuff. You wanted to answer all these questions without having to draw a picture. But after you answered the questions, it was always a good idea not to draw the picture, or at least do it on your graphing calculator to see if it confirmed all the stuff you just said. That was when it was just simple XY stuff. That was stuff that was all functions. We're dealing with stuff that are no longer going to be functions in the XY world. There is no reason to ever change it to polar if it's a function in XY world. There's no advantage to changing it to polar. But if it's not a function in XY world, but it's circular, I have x squared plus y squared, let's say, to some capacity. Maybe I'm raising it to a power, something like that. Then it makes a lot of sense to change it to polar. Now, what we're going to do next day is, like I said, find areas of things in polar, which is a little more complicated. So, let's do a little bit more with derivative stuff. Let's suppose that r equals, let's keep it really simple. R is the sine of theta plus the cosine of theta. I would like to find the derivative at every point on this graph. All right, so the first step we did, like last time, is what? What's dr d theta? Okay, so okay, what goes here? Times so what goes here? Sine theta? I'm just doing it in the order I gave you the formula. It's just easier to, I always do this. Like chain rule, right?
Oh gosh,
So what do I have here? Does that look right? So we have r cos plus sine times the derivative. And then what goes down here? I don't need you to memorize anything. I just need you to write it down correctly. Did we do it correctly? So what's this? R cos plus sine times derivative. This is negative r sine plus cos times derivative. Now, let's distribute it. Let's gather terms. Let's do whatever we can. Now, I would like to know what is the slope at every point. I didn't necessarily ask you where the vertical and horizontals are, but let's start by just figuring out the slope at every point. So we clearly want to distribute and gather terms, however much we can here. So what's this going to be? Sine theta plus cos squared theta. I'm sorry, sine theta cos theta. There we go. Plus cos squared plus sine theta cos theta minus sine squared. On the bottom, I'm going to have negative sine squared theta, negative sine theta cos theta, plus cos squared theta minus sine theta cos theta. Okay, I think we did it all correctly. Does this simplify nicely? I think it simplifies great. Let's do these guys first. What would this be? So cosine of 2 theta, and on the bottom, do I also have a cosine of 2 theta? Nice. Now on the top, sine theta cos theta plus sine theta cos theta is 2 sine theta cos thetas, or sine 2 theta. Oh my gosh, I'm gonna have the same thing on the bottom. Almost. So far, so good. Now, because all of my angles are 2 thetas, this actually would be a heck of a lot easier to set numerator and denominator equal to 0 because I have the same angle. That's a really good thing, isn't it? That's a really good thing, okay? So, this is the slope at every point on this thing. So let's figure out where's the horizontal and where's the vertical. Let's start with the horizontal. So I need my numerator to equal 0. Okay, so I need the cosine of 2 theta plus the sine of 2 theta equals 0. Or I could make it the cosine of 2 theta equals the negative of the sine of 2 theta, or I can go a step further. How about the negative tangent of 2 theta equals to 1? Ooh, that might be a little easier, huh? Make it simpler. How about tangent of theta is negative 1? So when is the tangent function negative 1? There's 2 places. So 3 pi over 4 and at 7 pi over 4, if I'm keeping it between 0 and 2 pi. Or you can just say it this way. 2 theta is 3 pi over 4 plus every multiple of pi forever and ever and ever and ever. I want to do it that way because we're going to have a whole bunch of answers, aren't we? Because that means that theta is what? Three pi over 8 plus k pi over 2. Ooh, those are weird looking angles. Those are weird multiples of pi over 8, but there's going to be 4 of them then between 0 and 2 pi. So I think between 0 and 2 pi, we're going to get then theta is 3 pi over 8. Now add 4/8. So 7 pi over 8, 11 pi over 8, 15 pi over 8. Okay? All of those places I'm going to get a horizontal tangent. Now, it may be that we're doing double duty like we did earlier. It may be that they end up being in the same place, but those are the actual numerical solutions. Now let's look at the denominator. I want a vertical tangent. So therefore, I want my denominator to be 0. So I want the cosine of 2 theta minus the sine of 2 theta equal to 0, or the cosine of 2 theta equal to the sine of 2 theta, or simply tangent of 2 theta equal to positive 1. Well, I know that's going to be pi over 4, and then every multiple of pi. So let's keep it simple. So 2 theta is pi over 4 plus k pi. So theta is pi over 8 plus k pi over 2. These are not the same angles. Not at all. They're the other eighths that are odd. So I'm going to get theta is pi over 8, 5 pi over 8, 9 pi over 8, 13 pi over 8. So far, so good? So I have 4 angles between 0 and 2 pi that will give me horizontal tangents, 4 that give me vertical. That doesn't mean there are 8 really, really cool points. It's very likely that we retrace our steps like we did earlier. Okay, it's very likely. So, anybody interested in figuring out what that looks like? Do you want to do it by a table? Do you want to pick values of theta and then plot the points? I mean, we can, there's nothing wrong with that. But then again, you're estimating root distances along a, if I said go about, pi over 3 root 7 units, it's kind of tricky. Well, how about if I multiply both sides by r? Is that legal? Yeah. Keep it simple. At 3 pi over 4, sine is positive root 2 over 2, cosine is negative root 2 over 2. So I gave you a place right there where r is 0. So a 45-degree type angle in the second or fourth quadrants will give me an answer of 0 here. So it's legal for me to multiply both sides by r. Why would I want to do such a thing? Oh my gosh. Give me an xy thing here. X squared plus y squared equals y plus x. How about if I do this? Can I complete the square? X minus what? Half. So what goes here? A fourth. Remember, you're squaring that value. Same here. So what do I do here? Whoa. I have a circle of radius 1 over root 2, centered at 1/2, 1/2. Whoa, that's not a weird looking graph. Or is it? Okay. So hold on a second. It's centered at, I said negative, excuse me, a half. Okay. I think I said that right. So hold on. And it does go through the origin. So on my graph, where is the origin? Probably about here, I think. I'll do the best I can here. A half squared plus a half squared is a half. And the square root of a half is 1 over root 2. So there's my radius. So see where the origin is right here. Now, horizontal tangents, 3 pi over 8. Well, isn't that pi over 4 exactly? That angle? So if I went out pi over 4, I'd be here. Did I say that? Am I looking at the right ones? Oh, I'm sorry. I'm going to pi over 8. If that's pi over 4, then pi over 8 should be half of that, and that should put me about here. Right? What would that one be? Well, I'm in the second quadrant now. Little more than 90 degrees. If that's pi over 8, then these are exactly right angles, aren't they? And that's 5 pi over 8. So what about the other two? They're the back and forth. So these two put me at the same position, these two put me at the same position. If you had tried to do this by plotting points, by making a table, do you think you would have got that circle? Iffy. I think it would have been difficult. Okay, now let's look at the horizontal tangents. 3 pi over 8, well, if that's pi over 4, then 3 pi over 8 should put me about here. Ooh. Okay, pi, now I'm all the way over here. Oops, no, the wrong one. where am I now? I'm at, the first one I just said was 3 pi over 8. I think the next one would have to be, well, 7 pi over 8 is here, but it would also make, let's see, 7 pi over 8 would have made my r negative and put me here. But I think it's also easier if I just go ahead and use the 11 pi over 8 also. Right. Doesn't really matter how I do it. I'm going to be there for 2 different places also. And then, again, it's a repeat thing. I don't need you to draw the picture, but I do need you to know that this is a circle. In fact, I need you to know that this is exactly this circle. Whether you draw it or not, it's not important. That you know how to convert it to here and here. So when you're seeing r's and sines and cosines, the trick of multiplying by r to make r squareds and r sines and r cosines, that's a really, really useful thing to do. It's very, very useful. Only if r equals 0, though, was already a solution, which in this case it was. And in a lot of cases it will be. Will there ever be, can I change this graph to make the multiplying by r not a correct move?
Plus a constant.
How big does my constant need to be?
Anything.
Anything bigger? Probably safe, just make it at least 2. Sine and cosine cannot both equal 1 at the same time. The biggest sine plus cosine can actually be is root 2. That's the largest that sum can ever actually be. And we can do that by just taking the derivative and setting the derivative equal to 0. So if you made any number bigger than root 2 on the right side, now that quantity can never be 0, so multiplying by r is no longer a legal move. Darn. That's not a problem you're going to have. Don't worry about that. Okay? It could happen. It's not going to happen. Because the problems we're dealing with are things that are probably really clean in nature. Now, understand where this is going. Next semester in 3D, we're looking at 3-dimensional surfaces. Right? That's why we did the rotation of axes. That's why we did all of this stuff with conics in the last chapter. Because now we're going to be looking at things in 3D where you're going to see x squared plus y squared. You're going to see things like that and go, you know, this might be easier if I change it to polar. And if you're having that thought, it's probably going to be easier. And things that would have been nightmarish in rectangular often become actually quite simple in polar. Things like finding volumes of things that are spherical in nature, you know, or finding areas between things. It's going to be something that's fairly routine, but you're actually not going to do it until about the last third of the course. It won't be necessary until about then. So what we're doing next day is the last lecture of the semester, the last new material. We're going to now do the integration part of the polar, which is not terrible. It's not terrible, it's not trivial. Because if you're integrating things that were not functions in XY world, that means they're probably circular in nature. Integrating things that involve sine squareds and cos squareds mean I'm going to have a lot of double angle formulas, and there's going to be maybe a little bit of icky algebra. But that's it, just a little bit of icky algebra, not terrible. So today's lecture and Wednesday's lecture, these are final exam worthy questions, but obviously they're not going to be on your next exam. We've already finished that stuff. So I need to remind folks, we have a test on Monday, then it's review final. Many of you will have earned an A, B, or a C. Most of you will have earned an A, B, or a C guaranteed after the next exam. But if that grade's not an A, then obviously you want to keep going and try to raise it. Automatically assume you're not getting the A. So therefore, do the remaining quizzes. Every semester it happens that people will say, oh yeah, I'm not going to need to do those last quizzes. And every semester, I will have more than one person in every single class who basically just threw away an A because they didn't turn in the last quizzes and they'd already decided they're not taking a final. And they missed it by a handful of points because they didn't buy. Don't be that person. Do your last quizzes, assume you need to do them, and then if it turns out you didn't, great, you can rejoice, dance in the aisles. But what happens is every single calculus and above class I teach, there will be between 5 and 10 people every single semester in every class that after the last exam, you will be quizzes away from the threshold of not having to take the final. Just quizzes away with 2 more quizzes due. So in this case, you'd be within, let's say, less than 60 points. But if you don't do those last 2 quizzes, you've just taken zeros on them and now you have to take the final to raise your grade. You don't want to do that. You'd rather have that, right? So do the quizzes automatically no matter what. Prepare for the exam because The review will start immediately after. I'm not going to talk about the review for the final next day. Next day, we're going to review for this last exam. I've already posted the practice finals. Anybody looked at it yet? Okay, I would almost rather you wait till after the exam, but yeah, take a peek, because after Monday, that's all we're going to do is we're going to practice those problems. By the way, the reason I tweaked the practice exam, I'd actually posted the wrong one. For many, many, many decades, I did certain things and didn't do other things in this class. And then several years ago, I removed a couple of items, and then I added a couple items, and then that's the practice test. And I always, let's go ahead and stop that.